Welcome to the third part of my lecture on scheduling in packet switches, following Shrikant and Ying's book, chapter 4. So today we'll talk about some low complexity throughput optimal switch scheduling algorithms. In particular, we'll talk about pick and compare scheduling and load balanced switches. Now, pick and compare is a throughput optimal scheduler which happens to be very low complexity. The complexity is order n, where n is the size of the switch. Now, here's how it goes. The switch first stores all maximal matchings. So, considering considering the complete bipartite graph representation of the switch, we index all the maximal matchings by h, by small h, lowercase h, and suppose there are capital H of those. So capital H is of course a large number. At time slot t, the switch selects the t modulo hth maximal matching and compares the weight of the old matching that it used and this currently selected matching, where the matching used in the time slot t minus 1 is kept if the old matching still provides larger weight than the new matching. Okay, so the idea is we go through the set of possible matchings one by one in a round-robin fashion, and then we don't change a matching unless the new one that we find is better. Now, why does this idea work? I think this is a very powerful idea because provided queues are large, then the relative changes in the queue lengths will be small from time slot to time slot. Thus, if you found a good matching with a large weight, you could roughly assume that the queue lengths are going to be still large and this matching still close to optimal in the next round. Okay, so provided that we are in this large queue length regime, the pick and compare algorithm will find the maximum weight matching within h time slots. Okay, and there is an exercise in the book that showing that this is sufficient for throughput optimality. The main drawback is that as we expect queue lengths to be very large for this throughput optimal performance, this obviously comes with large queue lengths in practice, which corresponds to large delay. Right. So the next architecture that we'll discuss is a load balanced switch architecture. This is even a simpler, even a lower complexity architecture, which also provides optimal throughput. It's a two-stage mechanism. In the first stage, we have this virtual switch, which evenly distributes the load to each virtual output queue. So these are the actual VOQs. This is VOQ. Is a VOQ 1, 1, 1, 2, 1, 3, right? But we basically have these buffers at the input working in a first come, first served fashion, and then they cycle through n different matchings in a round-robin fashion, which serve to distribute arrivals into each virtual output queue evenly. We'll see how this happens. And assuming that we've achieved this even distribution, in the second stage, we can simply go round robin and match each input with each output, this will work perfectly. So, what are these matchings that we use in a round-robin fashion? So, this is an example of a 3x3 switch, the first matching we use is this. Basically, it matches every input to the corresponding number at the output. And the second matching matches every input I to output I plus 1. But then 3 plus 1 is 4, so we take modulo 3 would be 1. So we have this matching. And then the third matching that we can have is I plus 2 modulo 3. So 1 plus 2 is 3, 2 plus 2 modulo 3 is 1, 3 plus 2 modulo 3 is 2. So we have these three matchings, and if we go through these three matchings one by one, if the arrivals are balanced, if the arrivals were balanced into the virtual output queues, it is easy to see that these using these three matchings will provide will provide high throughput, because essentially we are draining each queue at equal rate. Now we use these matchings twice, first at the stage 1 and secondly at the stage 2. So the aged matching is used at the first stage switch, so input port I is connected to output port J, which is I plus H modulo N, and if the head of line packet at input QI is destined to output port K, then the packet is transferred to virtual output Q JK at the second stage switch. And in the second stage, the aged matching is used again, and so on. So now it is easy to show that if the input to the switch, input into the first stage of the switch, destined to output J, is lambda 8J, the first stage will distribute the arrivals lambda 8J such that the total number of arrivals into virtual output queue IJ in the second stage is going to be the average of the arrivals destined to output port J arriving at each input port. Okay, so then clearly lambda IJ2 in the second stage, the arrival rate into virtual output queue IJ is less than 1 over n if the total arrival rate into the first stage queues is less than 1, which holds when lambda 1 lies strictly inside capacity region. So if we have an arrival rate matrix that is inside the capacity region, the load balancing is going to guarantee this even loading at all virtual output queues. Now at the second stage, virtual output queue IJ is connected to output J once every n time slots and can transmit 1 over n packet per time slot on average. Therefore, the virtual output queue IJ is stable, and we can make the same argument for all IJ. So clearly, this is then a throughput optimal switch scheduler intuitively, but for a formal proof of optimality, you can see the textbook. What is the drawback of this method? Well, packets may leave the switch out of order because when we are splitting, distributing from the first stage to the second, packets that arrive, one packet that arrives after another to go to the same output port may actually end up being ahead of the queue, ahead of the other one at the virtual output queue. However, this could be taken care of by keeping a reordering buffer at the virtual output queues. There's a nice extension to this, which is a randomized algorithm, which we can call randomized load balancing. It is the following, basically. Now, consider this load balance switch. Instead of applying the AND schedules in a round-robin fashion, each switch selects a schedule from the AND schedules uniformly at random. Okay? You can show, and it's in fact, the proof is going to be easier than the proof of optimality of the previous scheme, that this randomized load balance switch is also throughput optimal. Okay, so I think this is a lesson in showing us the power of randomized algorithms. So this is the end of this chapter, end of chapter 4. In the following lectures, we'll start chapter 5, which is going to be about scheduling in wireless networks. I hope you enjoyed this lecture. See you next time.